background, just
This meeting is being recorded.
Oh, that's loud. To tell people about how maybe ultra-low field systems differ a little bit from high field scanners that you might be more familiar with. So this is an example of one of these ultra-low field systems behind me. This is the hyperfine swoop that I've been struggling with for a couple of years now. So there's some significant parametric differences, and maybe one of the first ones to talk about is power usage. So in much of the world, access to three-phase power in the scale that you might need for MRI, you're talking about somewhere between 10 and 200 kilowatts of power to operate one of these instruments, whereas this, by comparison, is just plugged into the wall and uses maybe 600 watts of power in a typical use case. High field systems, of course, have a dedicated scanning room. It can get pretty large, and supporting that footprint can be difficult for many institutes, whereas this thing is about a meter squared in terms of footprint. You do still need a bed, but you don't need a control booth, and you can usually run these off a laptop, or even, as I have done in the past, from your phone, which is really weird. High field systems tend to be pretty heavy. You're looking minimum 3.5, maximum more like 7.5 tons these days. Older systems are heavier. This system here is about 600 kilos, but systems as light as 150 kilos also exist. And these mean that they can be put on the second floors of buildings. You don't need special reinforcements. You don't even need a special room. This doesn't have an RF cage. And I could be scanning with my laptop in the room. There would be no impact on it. And of course, there are significant safety changes that are associated with this. Projectile hazards from high field systems are serious, so is RF heating. In this, the RF hazard is relatively low, and the projectile risk is maybe a concern if you have gas cylinders, but otherwise not really. So going forwards, there are some other significant differences in terms of the physics. There's a couple of good points and quite a few bad points about low field compared to high field. The big one is T1 is substantially reduced. At this field strength, you're looking at maybe 200, 300 milliseconds. As said, sighting requirements are great. Don't need any cryogens. You can interrupt the power as much as you like. Because the field is so low, you don't really get a susceptibility artifact, which is something that people in diffusion imaging maybe are very concerned with. But this comes significantly at the cost of SNR. Compared to a 3T system, you're looking around 300 times less SNR per unit time. That's really kind of the killer going forwards for diffusion imaging, where SNR is king. And one of the things that is a problem here is that the gradients in these systems tend to be weak. Most systems, until very recently, have had gradients no more than about 10 to 20 millitesla per meter. And compared to diffusion, where 80 is considered by many groups, we would say that was the minimum to get something satisfactory. This is a serious issue, and it constrains the SNR further. And maybe another bad point is the magna homogeneity tends to be pretty bad. You might get a shim at 10, 20, 30 ppm on a high field system with higher order shims. Here you're looking at minimum 600 ppm just from the system itself and its homogeneity. And that changes the sequences that are available to you. So, maybe a fair question is, given all of these problems, why might we want to do this? Well, there are some substantial opportunities that exist. These systems could be cheap. These systems being cheaper means that scans can be cheaper. You can run larger studies with lower barriers to performing tractography, so that it doesn't have to be the remit of specialized research institutes. It permits scanning potentially in much more remote and rural areas, or less, should we say, economically privileged areas than we're traditionally performing scanning in. There's substantial improvements to safety, and when scanning children, the fact that you can have carers and dependents in the same room together can really help ensure that that scan goes without a hitch. And if you have someone who has problems with thermoregulation, or has implants, or has shrapnel injuries or something like that, they may be significantly safer to scan than someone than putting the same person in a high field system. So these reduced costs mean that study scale can look very different. A typical high field scan is maybe $1,000. It could be more, it could be less, but that's kind of the ballpark. But the projected cost of an ultra low field system being produced at scale could be as low as $50,000 to $100,000 alone. So we're talking about a system that could cost as much as it costs to run 50 or 100 MRI scans. The improvements to safety may, in the future, allow less expert operation. That's not a formal opinion, but I think, well, it is an opinion for sure. But I think some of the concerns around the safety, how we approach safety in MRI arise from significant projectile and RF heating hazards that are substantially reduced in these systems. And ultimately, studies with hundreds or even thousands of participants could be conducted for a fraction of the cost of a similar high-field study. When we look at the number of MR systems that are actually present in the world, we find it's very, very skewed based on where you are. When we look at somewhere like the US, you're looking at 35 systems per million inhabitants. And that's representing, what is that, 5% of the world's population, a little less these days. But if you go to India, representing 15% of the world's population, you have just 0.2. So you're looking at, what is that, nearly 50 times fewer MRIs per person. And that's actually more than that, bad maths. Okay, so, there are a lot of people that are being missed by MR studies, and the people that we are scanning tend to be people in urban, Western, wealthy conditions. And these underrepresented populations may face unique stresses, unique disease burdens that we're just not looking at right now. We don't have the means to study them. And if we did put MR systems in to study them, they could be potentially better used in healthcare applications. As said, carers and dependents can remain in the same scanning suite together. This is really desirable if you are scanning children, and when scanning those children, if they have issues with thermoregulation, as most children do, this is somewhat mitigated. Maybe it's also fair to say that most MR systems for ultra-low field are more openly designed, and that's quite favorable for claustrophobic individuals, particularly when they can remain in the presence of other people. Okay, so I just want to show you what two different scans might look like, a standard high field scan and a standard low field scan. So the high field scan on the left was collected on our Connectome scanner here with 300 millitesla per meter gradient, so it's maybe not as good as you might hope, but that's a B1000 scan, so it's a pretty typical representative image. Whereas the one on the right is one that we collected on this system, I think of me. And you may say, looking at it, how are you going to do anything useful with that? I can barely see that there's a brain in there. It just looks like an egg. Well, I want to say, wait and see. You might be surprised. I hope you'll be surprised. But looking at the parameters that were involved here, the scan that we collected on the Connectome took 12 seconds, whereas the one on the right took nearly 3 minutes. They both had a similar B value, very different gradient strengths, and fairly similar resolution in principle, though possibly not in reality, and fairly similar TE. So there's a lot in common going on here, but the image is substantially degraded. The EPI scan, of course, needs a very rapid readout to overcome some of the susceptibility problems, whereas the fast spin echo, because it's largely immune to these issues, can actually have a very long readout, 250 milliseconds plus. It does create other problems, but I won't go into it in too much detail. And again, distortions are principally arising from the B0 field itself rather than from susceptibility. So maybe I'm trying to stress here, susceptibility is a different concern to what it is at high field. And again, there are different echo pathways, different expectations with respect to motion. So it does get a little complicated sometimes to talk about these things and why artifacts exist in one and not in the other. In terms of sequences, we tend not to employ EPI at all at low field. There are groups who have demonstrated it, but getting the gradient performance is challenging, and getting sufficient bandwidth in that gradient, in that readout, can be tricky to actually end up with an image with enough SNR to build an image, which isn't just noise. And this means we tend to use fast spin echo sequences, which aren't a million miles off an EPI in fundamental premise, but involves this train of refocusing pulses. This actually creates a bunch of complications. So basically, I've done a lot of complaining. We have to ask, is high quality diffusion imaging even practical at ultra low fields? Well, I would say yes, with caveats. It is possible, but it's a matter of compromise. And I want to say that these compromises are fairly familiar. It's about reduced resolution. It's about lower B values. It's about accepting that it's going to be less SNR and tolerating a little bit of artifacts induced by motion. And maybe something I should have said here is it's also about accepting that it'll take longer. So again, I won't go over those parameters again, but you should know that generally speaking, we're not accessing the same resolutions. We're talking 3 or 4 millimeter isotropics. We're talking p-values of 600 or 1,000. Going up to 4,000 or 2,000 isn't practical. SNR is typically 10 or maybe even a little lower, whereas it's normally a lot higher for standard EPI. And TEs, again, are actually fairly similar. So in terms of resolution, what's the impact of this resolution? Well, low resolutions actually make nonlinear registration quite tricky. It can be difficult to tell exactly where one tissue ends and another begins, and so fluid registrations may sometimes fail where they might work better at high field. You can't generally construct high-quality fractional isotropy skeletons to co-register to T1s, and that's kind of a concern. You run into issues with multi-fiber voxels because, of course, they have different signal contributions, and that means that techniques like DTI tend to fail as you go to increasingly high resolutions. And all of these issues are exacerbated by something I was hinting at previously, which is these long readouts are allowing T2 decay to happen during that readout, and that means you end up with a broad point spread function, blurring in the voxels. So obviously SNR is impaired badly, so you end up with a very high noise floor. And this means that in general, if you are doing DTI, your tensors end up squashed, your fiber orientation distribution functions end up broadened, and you end up generally underestimating anisotropy. So, you know, the things we should be familiar with in tractography anyway. So I want to give you a little tiny bit of history of our investigation in this, because we actually only started in 2022. So we're talking about 3 years of study on this so far, and I think we've come a long way in that time. So this is actually our first successful tractography. You know, my colleague Alex Plumley was working on this at the time, and you can see it's pretty hairy. You know, yes, there's anisotropy that you're familiar with. You can see the forceps okay. And actually, you can even do some tractography. You can see that the callosum and CST are present in kind of the right shape. But I would like to say we have a little bit of improvement yet to do. So, you know, by next year, the images had improved in quality as a result of some enhancements to the denoising that was being done. And by that time, in an hour and 15 minutes and in a 9-direction scan, going to increasing numbers of scans, that's the theme going forwards, we were actually able to obtain this 2.2 millimeter isotropic scan. And okay, I see contrast, but I think the contrast is largely arising from the V0, which is describing what the underlying T2 is in the grey and white matter. So jumping forwards a year, we start messing around with increasingly large numbers of directions using this extra SNR that's available to us. And we attempted our first constrained spherical deconvolution. So this is a 15-direction data set, again, an hour and 15 minutes at 3 millimeter resolution. And you can start to resolve a lot more contrast than we were seeing previously. Again, there's a lot of diffuse blurring, there's a lot of funny colors in there that don't look right. And these biases are things that we've continued to work on in that time. But critically, this was CSD, and that means that we were able to see crossing fibers. And crossing fibers are, of course, something that's quite important going forwards in tractography, because it means you can accept, you know, interdigitated configurations of fibers, you can accept dispersion, and all of these properties that are otherwise not necessarily resolvable. So this resulted in a substantial improvement to the tractography that we were able to achieve. And you can see here that, you know, a little bit of say whole brain, this is really just the corpus callosum and CST, but there's something in there. And, you know, again, this was last year. So we might say, what actually changed? What did we do? What was the difference, and why did it look so different? Well, improvements in image quality were central to this. Deep learning regularized reconstruction techniques have improved and come a long way in the last few years. And I'm sure everybody working with clinical scanners is aware of that right now. You know, you have your deep resolve boosts and so on and so forth. And they do help, and they are appropriate to use, I would say, in diffusion imaging, even though they do come at costs. Improvements in nonlinear registration in terms of technique at our end made a big difference, and I'll go over exactly what we did going forwards. The shift to constrained spherical deconvolution is super important for tractography, and specifically using multi-tissue techniques in combination with anatomical priors. And again, with those anatomical priors, we also have anatomical constraint in the form of the tractography itself. So ACT tractography, multi-tissue CSD, better registration, and improvements in image quality have all led to substantially improved ultra-low field tractography. So I want to ask, I've talked a lot, I haven't actually seen a lot of tractograms yet. What's reasonable to expect? Well, I want to say, you might think looking at this thing that this had come from a high field instrument, or maybe a slightly older low field instrument, or slightly older high field instrument than maybe one of your premium systems. But no, this came from the scanner behind me, and this was acquired in a tolerable scan duration of, I think, 59 minutes. And again, these are detailed, fully fleshed out tractograms with a lot of the features that you've come to expect from high field systems. And again, the anatomical constraint that is present in the form of T1s and T2s is very, very useful in working in these noise constrained regimes. And it's possible to obtain really quite detailed information. So maybe the fair question is, those tractograms, what's the underlying contrast behind that? Well, again, if we look at FA, we see maybe it's a little bit hairy comparing the same brain. You can see there's a lot of information that we're failing to resolve. These fine transverse fibers just aren't present where we expect to see them, but there's maybe the hint of something there. And looking at the color maps again, you can see things aren't working perfectly. There's asymmetry as well, which is actually a major concern going forwards. A lot of our work has been about trying to address these biases that are present in these images. But when we start to examine the anisotropy and we start looking at the orientation functions that we can compute on this, we see there's a lot more contrast than maybe is at first visible in the DTI. And you can see, looking at these carefully, a lot of fine features are present that, again, don't show up in the DTI, but you can also see the impact of that broad point spread function, where anisotropy tends to bleed into adjoining voxels. So addressing and facing that compromise is very much central to the question of doing tractography at ultra-low field. On the basis of this, it's possible to do whole brain tracking with a lot of different techniques. Generally speaking, we actually adopt iFOD2 as our standard whole brain tracking, for a quick run through, and you actually get perfectly nice results. And you can pull out individual tracks by manual ROI selection, as you might see if you have a quick look at the paper associated with this that we've recently, well, it's preprint right now actually, so if you want to look at the preprint, go for it. But once we start to involve, deeper anatomical priors, deep learning anatomical priors in the form of TractSeg, we can see that we can pull out really quite detailed tractograms. And I mean, just watching this for a moment, you can see a lot of these are features that you have come to expect, and you should be seeing in anatomy in general. And it's easy staring at this to think, okay, fine, we did this on a high field instrument. No, this is on a system that cost us, when we got it, something like £200,000. I'm not sure what that translates to in dollars at the time, but not a lot, not something that you would pay millions for. And it's not a fluke. This isn't some mega compliant participant. This is something that you can expect to see in more or less everyone. And whole brain tracking is pretty consistent on these systems. Again, this is using TractSeg to show it slightly more clearly, but that's just because I think they come out a little cleaner when you look at the whole brain tracking that we do with anatomically constrained tractography. You get more tracts, but sometimes it's a little harder to disentangle them with your eyes. Okay, so a fair question is, we're using these deep learning techniques. Should we trust them? Is that appropriate? Well, if we use TractSeg in two different ways, we look at the tract orientation mapping that we do, and we look at the actual segmentation that's associated with TractSeg. We can use those to filter anatomically constrained tractography that we've done anyway. And when we look at those filtered tractograms, just using the regions that we're automatically computing using TractSeg, we see that there's a close correspondence between those filtered tractograms and the tract orientation mapping done by TractSeg. So I think there's a basis to think that TractSeg has some consistency with the prior that's associated with manual tracking. And when we start looking at whether tract orientation mapping is substantially realigning the vectors associated with a particular tract, actually we can see that the answer is sometimes a little bit. There are some deviations that it fixes, but in general, actually the overarching theme is no, it's not doing a huge amount. It's not over massaging the data to make it fit a prior. And even when we look at complex tracts like the archifasciculus, we can see that there are regions where this deviation is significant, but generally speaking, it's not on the whole, and most of the tract is left untouched. So maybe another question is, why would we want to do tractographic data why would we want tractographic data in the first place? And obviously when you have lots of SNR, you maybe have slightly different things that you're interested in doing, but the big thing is, of course, statistics, populations, large-scale measurements. And when we start looking at repeatability, we can see that actually FA is generally fairly repeatable. If we perform the same scan on the same participant on 2 different dates, we don't see a massive deviation from tract to tract and from person to person, from session to session. And this is thanks to my colleague, Will Royer, who's been working here on actually validating and making sure that these pretty pictures have meaning. And it's beginning to look like they probably do. And we see that trend is also present in mean diffusivity. Again, looking at populations, we can of course talk about distributions and distributions of FA. And again, you'll see the actual values for FA here. I mean, this is 0.2. That's very, very low compared to what we expect to see. And that's that noise floor coming to squash those tensors down and make them a little bit less interpretable than they used to be. So even though the contrast is present, the explicit numerical values that we end up computing might not have the same quantitative interpretations they do at high field, where SNR is better. Likewise, the MD kind of pretty much tracks that. Of course, this means that we can construct template brains, and these template brains are actually pretty nice, all things considered. I think this is pretty fantastic, given what we started with. And if you remember that first image from 2022, you can see we've come a long way. This is 6 subject image twice, so we have a total of 12 scans mashed into a single one here, and you can see a lot of fine features here that aren't present in individual scans start to appear in this large ensemble. And as you scrub through the brain, you can see more detail there. Of course, another thing that we can do is, as we've reduced the amount of time that we're doing for these scans, so most of the scans I showed you took around an hour, but we can reduce that, get a little less detail, but potentially collect other contrast information. For example, here we've collected simultaneously magnetization transfer contrast, and we've overlaid that over the superior longitudinal fasciculus. So you can see magnetization transfer imaging is also possible. Alongside that, likewise, we can do quantitative T2 mapping, which gives you a little bit of extra meaningful information that you can say about how different tracts are changing and developing under disease and stress. And of course, because we're doing diffusion imaging, we can always do quantitative mapping diffusion parameters along tracts. It's free, might as well. So, there are certain options that are always available to you in terms of tractometry. So if you're going to do tractography, you can always think about doing diffusion tractometry. Okay, so I've talked about some of the use cases for it, but how would you do this yourself? How do I do ULF tractography at home? And potentially it could be at home. The systems are pretty small, and I've seen people put these in vans. I've seen people even attach them to the back of a bicycle and cycle them around. There's a photo of Andrew Webb doing that. So the big thing, of course, is image quality. You need to maximize that contrast to noise ratio per unit time. And that means oversampling in your phase encoding direction. Again, we do multi-shot imaging. We don't do single-shot imaging, and that means oversampling is to some degree something you always have available as an option, because you can always collect more information. You're looking at oversampling ratios of between 200% and 300% as being reasonable numbers for this. Obviously, you need to choose an optimal p-value. That's always true anyway, but T1 and T2 vary at low field, so choosing appropriately is important. Generally speaking, higher is better, but once you go too high, you start to drop off and you hit that noise floor pretty quickly. You're looking at a preference towards isotropic resolutions versus anisotropic resolutions. That's not just because tractography struggles with anisotropic voxels. It's actually due to the nature of what K coefficients look like and the shape of K space itself, where signal starts to drop off as you go to those higher and higher K coefficients. And that means it's difficult to sample them at all at ultra low field. And so it's kind of advantageous to stick in a smaller sphere of K space. And this enables you to have longer echo trains. You can actually get up to 70 individual echoes with 4 millisecond echo spacing, but that's only really possible once you start dialing the readout bandwidth up fairly high. So stronger gradients are advantageous in that kind of context as well, because they help with that bandwidth. And you really need to keep that ESP down low. But as said, no matter what happens, it's a long, long readout. T2 is decaying the whole time. That PSF is going to end up pretty broad. And so you have to accept that there's some spatial averaging involved here, which is undesirable. And maybe some future techniques, diffusion-weighted SSFP, might help to overcome that because it's not vulnerable to the same defect. So in terms of registration, I hinted at it previously, but we can't use EDDI. It doesn't really make a lot of sense to use EDDI. This isn't EPI. We can't talk about top up. We can't talk about different distortions existing in different directions in the same way. But the underlying premise behind EDDI of there being some Gaussian model that you can use that allows you to account for major outliers and account for deviations and combine them in an intelligent way, that's still well-founded. And while we've attempted to use EDDI without incorporating some of the more eddy current specific, susceptibility specific functionality, we've never really been able to get into great registration compared to nice flexible nonlinear tools, boring stuff like ants. And this actually works pretty well for us because you don't have these susceptibility artifacts which are subject specific. What you instead have are global deformation fields that arise from B-naught inhomogeneity. And that means that generally you want to be favoring elastic deformations versus fluid deformations. So going forwards, you need to ensure that that's the kind of regularization that you're doing to get meaningful registration done. For orientation modeling, as I've said previously, CSD really supersedes DTI. I know it has for a long, long time at high field, but this is also true at ultra low field. Maybe that's unexpected when hitting those high direction counts is difficult. On this system, we might use 18 directions as a typical number. Sometimes a little lower, sometimes a little higher, but 18 seems to be the sweet spot right now. It's very desirable to collect matched anatomical data. So, we usually just collect a fast T2 that takes about 5 minutes or so. And that gives you enough information to do multi-tissue constrained spherical deconvolution. The spherical harmonic order is usually kept pretty low. It's not surprising. We go up to about 4. And it's usually a good thing to keep that non-negativity regularization quite strong, because again, you're going to get some anomalous voxels and you want to scrub them from existence. You don't want to include them in your fit. Okay, so I've wandered on for a bit, but I can talk a little bit about some of the future of ultra low field diffusion weighted imaging. Well, it's got the same title. Higher gradient strengths are possible. So when you think about gradient duty cycle, going to higher and higher gradients doesn't necessarily mean that you're going to substantially change the total amount of energy that you end up depositing in those gradient coils. These systems tend to be passively cooled. And a passively cooled system, obviously it's going to heat up substantially. An hour of scanning on this thing pulls it from about 20 degrees centigrade up to nearly 33 degrees centigrade. So, it's a 12-degree shift, and the thing will shut off at 35 to avoid burning someone. So you can't do a massive amount of diffusion imaging before you overheat these things. But when you look at the mathematics behind it, you see that for a given B value, the total energy involved is more or less determined by the B value, not by the overall strength. But you can hit that B value faster by going to a higher gradient strength. And as a result, shifting to a 40 millitesla per meter gradient means that TE can be pulled down from about 80 to 50 milliseconds with about the same energy deposition in the coils. And the difference in that is really to do with the gradient power amplifiers. And as improved inverters and improved inverter semiconductors like gallium nitride have started to become available, this means that we can hit higher gradient strengths without really compromising anything. So there's a lot of room to grow here. And this is obviously going to substantially improve the signal-to-noise ratio, and you can get far higher quality diffusion imaging. So ideally, we want strong gradients. I mean, this doesn't sound like a particularly exotic thing for someone into tractography to say, but strong gradients are good. And when we look at the kind of images that we can get from that, and again, you compare those to those images from 2022, you can see it's a really, really far cry from what we started with. And you can see all kinds of contrast that we weren't able to see. You see singular, you see these nice superior association fibers. You can see a lot of fine structure that was otherwise missing. So we have a lot of hope. And of course, the tractography benefits substantially as well. And whole brain tracking starts to look really realistic and desirable. I just want to touch on one final point after this about motion and cardiac pulsatility. Again, this is a bit of a dry topic, so I won't linger on it, but cardiac pulsatility is actually pretty important. And it's important because this is multi-shot imaging. Diffusion is a motion-sensitive regime, and phase errors accumulate between shots. And when we combine shots, it results in potentially destructive cancellation of signal. And just because we collected it correctly in one shot doesn't mean the combination contains the same information. Now, with appropriate motion state consideration, we can actually think about collecting data which is only in the diastolic or systolic phase, not with gating, but with retrospective binning. So in order to collect these images, we used a off-the-shelf pulse oximeter, connected it to a Raspberry Pi, nothing exciting. And again, because this is a low-field instrument with $50 of equipment, we were able to do full retrospective binning of the available data here. And nothing super complex went into that. And you can see that these huge dropouts aren't present when they're collected in the diastolic phase instead. And you can even potentially do this using time-resolved diffusion-weighted imaging. Maybe there's even an application associated with time-resolved diffusion-weighted imaging at ultra-low field. You can see the severity of the dropout artifact as the pulse happens. I hope that shows as well for you as it does for me. And of course, the thing about these dropouts is they do depend on the diffusion encoding direction. So we're going to see somewhat complicated biases that are present in almost all of the images that I've shown you that have been affected by this artifact that at yet is not being corrected. So with the implementation of this correction, I hope that we will see substantially improved tractography going forwards too. So on that, I just want to conclude by saying, yeah, you can get sensible quantitative measures if you're prepared to do a little bit of correcting, a little bit of messing around. You can totally get viable DTI, viable CSD, and viable tractography, all at ultra-low field on an instrument that didn't cost a lot. You can do concurrent tractometry. There's enough spare time left over within that kind of hour-long window. And so you can get function-specific measures that maybe might be difficult to obtain otherwise on anything short of another high-field instrument. And finally, I want to stress, pulsatile motion is important. Please care about it. You need to fix it in order to work well with ultra-low field multi-shot diffusion-weighted imaging. So thank you very much.
Thank you, James. That was a very nice overview of all the work you've done, and also think of where we're at with low-field tractography. So I think it's a super interesting topic, and so I hope we'll have a lively discussion. I think what has helped in the past to sort of like get people to join the discussion more is if you could all turn your cameras on. That would be nice. And I am encouraging anybody who has questions to please just join in and ask their questions. If there is none, I can get the discussion. Does anybody have questions? All right. Okay, so, please, go on, Max.
Yeah, thanks, James. Amazing talk. Lovely to see these images come out and these tractograms and bundles. You mentioned constraint spectral convolution as being very promising and exciting for tractography and crossing fibers. It's always a bit of an issue, especially in multi-tissue CSD, to get your response functions right and tune them and estimate them from the data or from priors. And if your DTI or your diffusivity estimates are not that great or a bit noisy, that means your response function, in a sense, is also a bit noisy or not that well estimated. So what's your experience on this, and is there something to do on ultra low field images that we don't do just with the defaults on the standard
So I would say,
MRI?
yeah, I would say that's certainly been an issue for us. We've found that generally using response function estimation actually is fairly robust using algorithms like Chantal Tax's method. It does tend to select appropriate voxels, but manual selection of voxels is not such a terrible choice in the first place. So selecting a small number of voxels from that anatomical prior that you know are going to display relatively single fiber content seems to work fairly well. That's been my experience. So manual methods and automated methods, neither has visibly outperformed the other in my reckoning so far. I do think that there's room to improve on the methods that we're employing right now on that, though.
Okay, thanks.
Christian?
Yeah, that was really interesting. I guess two questions. One, if you looked into your crystal ball, your scans are still taking about an hour, a bit more than an hour, I believe. How short do you think you might be able to get that scan time to, if you know, in a few more years when you've implemented 5 more corrections that you haven't told us about?
So thankfully, I can look into that crystal ball, and I can imagine a time, sometime around May next year, when hopefully we'll be able to show you some imaging done with admittedly only 9 directions in about 15 minutes. Now, I don't think the kind of quality that we are talking about for a lot of the scans that I've shown will be looking like that in 15 minutes, but I think we might see that number down as low as 30 going forwards. Is not a crazy number. Again, with improved gradient performance, you really can improve SNR to a substantial degree, and that's the name of the game here. So I'd say 30 minutes is a reasonable figure to look for in the next few years. Maybe after that, we might see bigger improvements as image reconstruction techniques improve.
Okay, and I guess my second question is, it's, the 64, 68 millitesla, is it's pretty arbitrary value. I mean, is there any potential, I guess, you're using a specific system right now of that increasing while still maintaining a lot of the accessibility requirements and so forth, because obviously that would give you a lot of those benefits back, and if you can, with the technical advancements and so forth, like, is there any kind of options for that?
Yeah, I would actually say the idea of a higher performance system, specifically maybe for these more neuroscience investigatory questions rather than clinical questions, is viable. I've seen a 110 millitesla system being demonstrated before. I think that was it was around 800 kilos. So it's a pretty big system. You can't go above certain numbers because the remnants of a rare earth magnet is only so high. And so, the density with which you can pack them eventually constrains the size of the field that you can build. So it depends in a big way on magnet geometry. It depends on the weight of the system, how many magnets you're prepared to put into the system, which is linear with the cost. So I would say going forwards, it wouldn't surprise me to start seeing higher fields, 100 millitesla systems with higher performance. And at this field, that results in a boost in SNR per unit time of probably that should be nearly 2.5. So that would substantially reduce scan time or improve quality.
Great, thank you.
Anybody else? I can go with a big picture question that it doesn't necessarily have to be just for you, James, but maybe for everybody here. So I feel like in general, we struggle to get for normal field tractography actually used in the clinic, at least for what is like non-surgical planning purposes. So I would say, where do you see the sweet spot for ultra low field tractography, and do you think that its integration actually might help the diffusion rather than the point of tractography in clinical settings? That would be my first, and then I have a second one, which is many people, like including me, work at the other end. So with like high gradient systems, I don't know, on the connectome scanner, and we look for finer, like very fine structures. So I'm curious to know how you and all of us like see these two sort of like ends integrate in the future.
So, I mean, I can definitely offer an opinion on the first question, hopefully the second too. So I think in clinical contexts, one of the challenges with low field systems is that you can't really do fat. So you can't do fat-specific imaging. You can't really separate the signal from fat from water in a meaningful way. And you can't do susceptibility-weighted imaging. And that means sometimes it is difficult to establish the difference between, e.g., necrosis and inflammation following stroke in that kind of context, or suffering following trauma. I can imagine the use of tractography as a means to establish whether there's substantial deviation of brain tissue, maybe in developing context too. When I say deviation, I mean deformation associated with the inflammation. I've seen that used in other clinical contexts, but again, that's something that I'm not really I'm definitely much more of a physicist than a clinician, so you can't quote me on any of that. It's just my opinion. Maybe someone else has a better statement on how this could be useful going forwards. But if not, I'm happy to have a crack at the second one, which is fine detail. Yeah, I mean, fundamentally right now we are using a few little machine learning tricks just to improve our tractogram quality. And I would say those are the beginnings of the incorporation of, so the knowledge that as you move towards the cortical surface, that you should see this dispersion taking place. That's an example of that fine detail being recovered from an anatomical prior. So I would say going forwards, I'd like to see more involvement of other contrasts alongside diffusion as a means to resolve fine detail that's otherwise not resolvable because of resolution limits. Just an idea, but...
Yep, please, William.
Sorry, can I ask a question? That was a great talk. I'm not sure I understood much of it, but that was me, not you. So I'm interested in using low field for monitoring an operation, okay? So I wouldn't need huge anatomical detail. One of the things that it would be useful for would be just to, if I'm infusing a fluid into the brain, to see the extent of the distribution of that fluid. So do you think that that's going to be technically possible? I mean, it's not tractography, but it would be a much cruder estimate. But I would be really interested in seeing how the distribution of a pure water, for example, not that I'd ever want to put in pure water, but how that would diffuse to the brain in a reasonable time scale. That's one question. The second one is, if I prang something I shouldn't prang when I'm putting a needle in and it bleeds, is low field able to detect that kind of change, that an acute blood clot, for example, not just distortion, but the actual presence of blood? Would that be possible?
So I can answer the second one very quickly. Generally speaking, no, it's difficult to resolve hemorrhage at low field, and that's a big downside. You don't have access to T2 star contrast in any meaningful way, so you can't see blood going anywhere it's not supposed to, and you can't really see clots unless they're large enough to be macroscopic on the voxel scale. In terms of contrast, yeah, actually, I would say there's some fairly exciting developments in terms of. So I have seen some work on paramagnetic contrasts in ultra low field systems, but maybe more exciting would be incorporating hyperpolarized information. So hyperpolarization and low field kind of go hand in hand perfectly, because the downside with the low field, of course, is that you end up with weak spin bias, and so it's difficult to resolve a strong signal. But with hyperpolarization, of course, even a tiny amount of not particularly well polarized material is still biased far more strongly than the water molecules will be. And so you can imagine a bolus of some suitable polarized material showing up in some detail perfusing throughout the brain. So yeah, I would say so. I don't see why not.
Well, we might have a chat. Thank you.
Brilliant.
Anybody else? Any question, comment?
Complaints?
Yeah, plain request.
Well, maybe a small comment, Chiara, on your question on the clinical maybe application. I see a lot of potential, especially when you start rolling out in low and medium income countries and make MRI more accessible to develop really what we're starting to see in the literature as called brain charts, or these normative reference of, let's just call it healthy white matter. And James, you showed us quite strikingly that a method such as TrackSeg works well. And so you can imagine that you have this tool to essentially have a fancy way to define regions of interest in which you have a notion of what is a normal reference for a 30-year-old white male or Indian male on the battlefield or in Africa or anywhere. And then you have that knowledge and you have that system that can assess now if you're deviating from that curve. And I believe that this will be extremely useful information for medical doctors in the future if they start integrating this information in their practice and in their patient assessment. And it'll be just easier to do, even if it's low res or a little bit less high resolution than the standard 3T or 1.5T images. So that's my take on it. I see great potential for that and bringing this more and more useful and easy to use.
Yeah, I mean, I think that that's certainly the case, and I think Derek, I mean, made a brief statement on what the actual, why we actually started mucking around with this to begin with. This Unity project was looking at neurodevelopmental targets in the young, and I flagged neonatal imaging a couple of times, but we were funded by Gates, by the Gates Foundation, to basically look at how children under different environmental conditions might go through aging differently, and diffusion as a means to do that is not a crazy thing. Oh, Derek apparently only sent that message to me, and I shouldn't have said that Derek asked me to ask it. Whoops. Sorry, Derek. So yeah, I would say looking at healthy development and looking at development in challenging conditions is a great example of something that's highly suited to ultra low field imaging, where you can do imaging at scale, and do lots and lots of scanning where otherwise you might only do 10 or 100 or 50 scans. So you can start to see averages that might represent populational variation in the impact of different stresses that might otherwise be invisible because you didn't catch enough of those that were subjected to high stress conditions versus low stress conditions. So scale kind of comes with its own benefit. I think that's one of the things that's exciting about ULF.
Great, thanks.
Brilliant.
Maybe this is not that interesting, but I know you have shown that, like, just following up on that, on the building like this normal or like normative data sets. You have shown that the measures that you obtain are reproducible, and I don't know anything about ultra low fields, but I wonder how stable, like, I imagine they're less stable than our like conventional system. So how much does that stability like influence your reproducibility, or do they need to be recalibrated? I don't know. And how would that impact?
So we had a recent study which was looking at measures of T1 and T2 in phantoms across, I think it ended up being nearly 12 different sites, all across the entire globe, all on scanners with slightly different versions. And yeah, very highly reproducible. If you want to know a bit more about that, I'd have a look for Beatrice Lina and Emil Lundberg 2025 just got published. So for those measures, I'd say highly reproducible. For diffusion, I think that the implicit quantitative property of diffusion really works in our favor. And I think we can possibly expect to see more reproducible information than T1 and T2. But that's just an opinion from me. We'd have to verify it to know for sure. So maybe we can follow up with a paper doing the same phantom study in diffusion instead.
Great. Anybody else? No? Well, if not, I think we can end early. We can thank James again. Thank you so much. This was great. I actually, this is my, sorry, my bad, but I'm not prepared to announce what the next Tract-Anat will be. So just, I wasn't prepared for this. Look out for an email from me or Francois about what the next Tract-Anat will be, and we hope to see you there. Thank you for joining. Bye, everybody.
Thank you, everyone.
Have a good rest
Bye-bye.
Bye-bye. Bye-bye.